Hello everyone, this is Group 7, and welcome to our presentation. Today, we will explore the boundary between the mechanical precision and the intelligent adaptation. Our team is composed of 6 members, and my name is Feng Zhou, responsible for the introduction. Longinbo will work on the two-stage training and the policy fusion method. Li Pei handles the optimization process, and then Peng Yuling and Wang Xilong will talk about the experimental setup and the result. Finally, Liu Xiahong will analyze the challenge and the limitation of our approach. Let me start with the question. Is the end of the tradition control the starting point of the intelligence? Traditionally, we have relied on the PID controls, the trajectory planning, and the finite state machine to guide the robot behavior. This method work well in the structured environments, like the factories, the assembly lines, and controlled labs. But what happens when the environment is unpredictable or the opportunity is unknown? So here comes a real challenge: is how do robots learn to capture change when the rules fall? That's where the deep reinforcement learning opens a new path. Rather than the hard coding and remove, we let the robot learn from the interactions to fall, to adapt, to win. When the action outcomes are non-linear, the delayed, and or the uncertain, learning becomes more powerful than planning. So here we ask a deeper question: can robots act, play, and adapt like humans? We believe they can. At least we are getting closer. The deep reinforcement learning allows the robot to learn the agile locomotions, like running and balancing, the tactical decisions to make to adjust under pressures. Some skills compositions reuse the learning behaviors in the new content, and even sim to real transfer, take what to learn in simulation into the physical world. In this project, our groups invest how the pilot training and the fusion technique allows robot to make better decisions in the dynamic environment. Let's begin our journey from the rules to real intelligence.
My name is Longinbo, AIT306 Then I will explain the two-stage training pipeline and policy fusion mechanism used to develop agile soccer skills for a bipedal robot. We began with stage 1. In this stage, the robot learns two essential behaviors separately. The first is the get-up skills, which enables the robot to stand up after fueling. The second is the soccer skills, which includes walking, turning, and kicking the ball. This separation reduces task complexity. After both skills are pre-trained, the training moves to stage 2, where a single unifying policy, denoted as PICETA, is trained to handle full 1v1 soccer scenarios. The details of this fusion process are introduced in the next slide. To fuse the get up and the soccer skills into the unifying police PICETA, the authors use a method called state-dependent skill distillation. When the robot is standing, it imitates the soccer skills. When fueled, it follows the get up skills. This is implemented using KL regularization. The loss combines two parts, maximizing expected value and minimizing divergence from the experts. A dynamic weight lambda controls imitation strength. Early in training, lambda is high to enforce close imitation. As the policy improve, lambda decrease, allowing more freedom. This balance initial guidance with later optimization, leading to faster, smoother learning. To enhance strategic ability, the training includes self-play. The agent compares with earlier snapshots of itself sampled with the first 25% of training. This lets it adapt to stronger opponents gradually. As a result, the robot moves beyond basic skills and learns intelligent behaviors. Let's conclude the explain of the two-stage training and policy fusion process. Then Li Pei will show you our policy optimization.
Hello everyone, and I am Li Pei, and today I'd like to talk about the decision making under the uncertainty, especially in complex tasks like the robotics and sports. We will begin with the partially observable Markov decision processes, or the POMDP. Imagine training a robot to play a soccer. This robot doesn't have the perfect information about the game. It may not know exactly where the ball is or where the other players are at every moment due to the limited or the noise sensor. This is a typical POMDP scenario. Instead of observing the full state of the environment, the agent receives the partial observation, maybe just an image, a distant estimate, or some cue. These observations are uncertain, and the robot has to make decision based on the beliefs. Its best guess about what the true state might be. In such dynamic and uncertain setting, traditional decision-making framework like the MDPs for short, we need models that can handle ambiguity and help agents act wisely even when they can't see the full picture. But modeling uncertainty isn't enough. We also need to optimize policies effectively under the uncertainty. Many standard reinforcement learning methods focus only on average outcomes and can become unstable or risky in uncertain setting. We need smarter, more robust way to learn. This brings us to distributional maximum posteriori optimization. DMPO is a policy optimization algorithm designed for exactly this kind of environments. It improves decision making in two key ways. First, it uses a distributional queue function to represent the full range of the possible return from each action, not just the average. This helps the agent assess both reward and risk. Second, it uses a maximum a posteriori optimization. Instead of blindly maximizing return, it updates the policy in a stable way, constrained by how much it deviates from the previous policy. This makes training more reliable, especially in high variance environments like the robot soccer.
Hello, my name is Peng Yulin. Let me introduce the experiment setup. This study employs a method called sim-to-real, whose core idea is to first train an efficient control strategy in a simulation environment and then directly transfer it into a real robot for execution without the need for additional parameter tuning or fine-tuning. The OP3 bipedal robot used in this study has lower stability than quadrupedal robots, and it also has lower hardware costs and poor impact resistance. If training were conducted directly on a real robot, it would not only be inefficient but also risky. This places higher demands on the robustness and generalization capabilities of the trained strategy. The experimental environment is divided into two parts, a simulated environment and a real-world venue. In this simulation, the author used the logical engine to build a 5-meter multiply 4-meter soccer field, including two robots and a soccer ball. In the real world, they replicated the same sized venue in the laboratory, equipped with 14 OptiTrack cameras to construct a high-precision motion capture system that tracks the positions of the ball and the robots in real time. The simulation and the real-world environments maintain consistency in physical structure and perception interfaces to support zero-shot sim-to-real transfer. The robot used for the experiments was Robotics OP3. It is a low-cost 20 degree of freedom small humanoid robot that is 51 centimeters tall and weighs 3.5 kilograms. It is controlled at 40 Hz and the strategy generates 40 motions per second, each of which is a 20-dimensional joint angle target value. To enhance the smoothness of the motions, also introduce a motion filtering mechanism. All the computation of the strategies is done on the embedded CPU of the robot body with no dependence on the GPU. The sensory information is obtained from its own MMU and from an external mocap system. The strategy employs a policy-based reinforcement learned algorithm known as DMPO. The input data primarily consists of two components. First, the robot body perception Second, external environmental states. The strategy outputs a control vector at each step to drive the robot actions. The reward function is designed with great precision, incorporating intensive forward movement, ball control and scoring, as well as penalties for folding, knee joint overload, and other actions, thereby balancing performance and safety. The experimental setup ensures that the policies are both efficiently learned in simulation and safely migrated in reality. Next, we show the results after the deployment of the policy.
Hello, I'm Wang Xulong. I will talk about results and visualization. Using a two-stage deep reinforcement learning framework, the agent mastered dynamic walking, rapid recovery, precise kicking, and tactical decision-making. This learned policy outforms script baselines across all matrices on real hardware, working 181% faster, turning 302% quicker. Recovery time reduced by 63% and running kick speed increased by 34%. Now let's dive into the data. We can see the learned working speed is 0.57 meters per second and 0.2 for the baseline, and this achieved through a dynamic forward learning gate. Then we move and see the turning is 2.85 read per second and 0.71 read per second. The agent spontaneously discovered pivot spinning on foot. This is the pictures of slow motion of turning by the robot. Also, we can see the kicking. The running kick reached about 2.77 meters per second and is 34% more kinetic faster. Most importantly, this behavior emerged autonomously but not by human manually design. How do we decode the agent's complexity? Visualize and we can uncover that the baseline is mechanical circular path and it's the periodic gate. The learned policy is spiral, non-periodic structures, color clusters mapped to running, walking, and kicking. Second, the bright zone here equals to the high value states, which is the agent prefers ball moving towards the goal. When opponents block, like this picture, values plummets, this proving tactical awareness. Most remarkably, it learned curved paths to defensive ridge lines to intercept shots. In strategy scenarios, we have 100% shot blocking success. The trajectories here shows agent arcs to cut off angles. In the picture, the left one shows the real environment, left and right foot trajectories in defensive footwork. The orange line is right foot and the red line is left foot. And in the red picture, it's the long stretch trajectories for the ball chasing scenario. We can see the track points here are dense. It means defending the footsteps are close together. In the same, the track points sparse means when chasing the ball, the footsteps are far apart. Short steps when defending is about 30 steps, and the long stretch when chasing balls is about 20 steps. Look at the simulation to reality transfer. 70% successful recovery and shoot in simulation, and 58% in reality. Only 12% gap. This proving domain randomization is work. Without skill regularization, agents degenerate to rolling it shows the two-stage training necessity. In general, deep reinforcement learning equips low-cost BEPs with human-level motor intelligence, outperforming hand-coded tactics. All code and data are open source, accelerating the future of robot locomotion. Next, we'll discuss about the conclusion.
Now, I'd like to share with you the key challenges and limitations from this robotics project. One of the central challenges was bridging the simulation to reality gap. Real robots may experience problems like control delays or hardware inconsistencies, while the simulated robots are idealized and cannot model them accurately. The team addressed this by using high-frequency control, domain randomization, and external perturbations during training, leading to robust real-world performance. Another major challenge was skill fusion. Instead of learning isolated behaviors, the agent needed to dynamically switch between actions like walking and kicking on a situation. The solution was two-stage approach, First, train get-up and soccer skills separately, then combine them through self-play. The resulting agent showed emergent strategies, for example, stepping defensively to block an attacker or slowing its gait when approaching the ball. Despite the success, there are still some limitations of the project. First, the system relies on motion capture and there is no vision-based perception. This may limit deployment in real-world scenarios. Second is the inference latency. The network sometimes fails to produce actions in 25 milliseconds. That may affect the control frequency. Also, the policy highly depends on manually designed reward function. It will limit the versatility and transferability. And self-confrontation training still needs optimization for stable policy. This project demonstrates the great potential of deep reference learning in practical robot control, not only achieving autonomous learning of complex skills, but also showing good real-world transfer capabilities. It lays a solid foundation for building robots with human-like intelligence and motion capabilities in the future. That's all of our presentation. Thank you for watching.